Students, in this video I'm going to discuss Newton's method. Okay, now from the steepest descent method, which we have already discussed in previous video, we have seen that negative of gradient points directly towards the minimum only when the contour of the function is f is circular. So if you have circular contour, then according to the steepest descent method, because this method uses the negative gradient direction, so obviously in this case this starting point is this, your solution is directly towards the x star. Okay, so what we have observed here, that negative gradient may not be good global direction for any arbitrary nonlinear function. For circular one, this is well and good, no problem. But if your contour is not circular, for example this elongated curve, then this negative gradient direction is not very good. You can see that the slow convergence. So for circular, steepest direction gives you fast result, but if your contour is elongated, then this steepest direction is zigzag motion, and then finally slow convergence. That is the drawback of this method. Okay, so to overcome this drawback of slow convergence for this type of contours, what we have taken the second order convergence, because steepest descent method is a linear convergence having speed linear convergence speed. So here in Newton's method we are having second order convergence. So this drawback of steepest descent method is addressed in Newton's method by using second derivative rather than first derivative. Here we are using second derivative to create search direction and getting faster convergence. तो इसमें हमने सेकंड डेरिवेटिव का इस्तेमाल किया है. स्टीपेस्ट डिसेंट मेथड में हमने फर्स्ट डेरिवेटिव का इस्तेमाल किया था. ओके, सो हियर सेकंड डेरिवेटिव मींस हियर वी आर यूजिंग Hessian matrix. So Hessian matrix of the objective function is used. The basic idea of the classical Newton method is used and second order quadratic approximation of the function f of x about the current point xk is used. So what is this? So this is the Taylor series expansion. So if you will see in one dimensional basically f at x can be written as f at this x k. Here we are approximated our function about the point xk. Okay, so about the point xk we are approximated, so that's why this is f of x current point plus x minus xk. Okay, this is the, and this is basically denoted by delta xk. So what we can do, we can write this as xk plus gradient of xk. So now approximate. So if you remember what the in ordinary f plus x minus h, for example this, sorry, x plus h minus h, sorry, point is x, this is x naught plus x minus x naught. Okay, so this is the solution. That means f at x naught plus x minus x naught. Now this is well. Okay, so this is basically your suppose h. So what will be the expression? F at x naught plus x minus x naught h and f dash at x naught plus x minus x naught whole square divided by factorial 2 and second derivative at x naught plus higher order terms. So order of x naught, order of h means x minus x naught. So okay, h cube. Okay, higher order terms. So in place of now, here this can be further rewritten, which is approximately equal to f of x naught plus x. In place of x we are having h, so x minus x naught f dash x naught plus this can be written as x minus x naught by factorial 2 second derivative x naught multiply by its, because here is power 2, so x minus x naught. We have bifurcated into two parts, x minus x naught, x minus x naught. Okay, so we have neglected this higher order term. So now in our case, in place of this, x naught is replaced by xk, x minus x naught is replaced by delta xk. Okay, so x naught is replaced by xk, x minus x naught is replaced by delta xk. So what will be the expression then? So the expression will be f of this term, but x naught is now xk, so that's why xk plus this term x minus x naught is this, so gradient this. So first I am writing this derivative, f dash at x naught is replaced by gradient of f at xk. X naught is what? Xk, dash means gradient. Okay, similarly second derivative at x naught, this is replaced by del 2 f at xk. So what will be the x minus x naught means delta xk. Okay, then we have first derivative means this term, gradient f of xk. Then we have second order term, this plus 1 by 2 this x minus x naught is this. So since this is a vector quantity, so that's why delta xk, this multiply by this term which is nothing but the del 2 f at xk. Then x minus x naught, this is delta xk. Okay, and here I am using transpose because this is the vector product. Okay, that's why this is a transpose, this is without transpose. So when you multiply you will have the square term. Okay, so this is the expression, so I think you understand how to get this. So we are using the Taylor series expansion and this is the justification. Okay, so now taking quadratic approximation, so this higher order term is removed. So we are having f of x is equals to f of xk plus delta f of xk transpose and delta xk. So here we have replaced this here delta xk, and here we are using the transpose just like here, because these are two vector quantities, that's why. So this is transpose and then this plus half delta xk transpose del 2 f of xk delta xk. This is nothing but, we know that this is denoted by hxk, Hessian matrix. So that's why f of x is equivalent to f of xk plus delta f xk transpose delta xk plus half of delta xk transpose Hessian matrix H at point xk delta xk. So this is equation number 1. Hk is the Hessian matrix. So now if you observe, this is the actual function, but the right hand side is the approximated function. So, and which is having quadratic second order approximation. So this is the actual objective function f of x, and this is basically the qx is approximated quadratic function at xk, because this is second order convergence. Okay, so now if you will take this is point xk. So at this point f and this both are having same point. Okay, so both are coinciding at this point and minimum occurs at this point. Sorry. So here if you will see at this point at xk plus 1 point, the minimum of the actual function and the approximated function, they are almost same. Okay, so now the idea is to determine the optimum solution to the approximate function, this function, and use this point to determine a search direction. Now to determine search direction to get minimum means optimum solution. So what we will do, we will differentiate equation number 1. So differentiate 1 with respect to each of the component of delta x and equating the resulting approximation expression to 0. This is first order necessary condition. So here we are differentiating here. Differentiating means this. So in ordinary case here this is f of x. So just differentiate this function f dash. So what we have, we are having this. So if you will see, I am rewriting this. F of x is f at x naught plus x minus x naught f dash x naught plus x minus x naught whole square by factorial to second order derivative at x naught. Now differentiate this equation. So f dash x will be, this is 0 plus from here we get 1. So simply f dash x naught plus from here we get x minus x naught f second derivative at x naught. Okay, now replace these ones. So what we will get in place of f dash means gradient. So gradient of f of x is equals to 0 plus here f dash x naught is delta f at xk plus here x minus x naught is this delta xk. Okay, and here we have seen, because in our case this term is equivalent to this term in our case. So when you differentiate this, so we will get this and del 2 f at xk. Okay, so this is the derivative in our case, in this case. Okay, so here we have written this. So delta f of x is 0 plus delta f of xk plus del 2 this. So here they are writing this first and then second, इसको यहाँ लिखा गया है delta xk, and आप इसको जब पहले लिख रहे हो तो you can use transpose here. So transpose delta xk, this is equal to 0 because here f dash this should be 0 for minimum. Similarly this should be 0 for minimum. So this should be 0. Okay, so this is equal to 0. So when put it 0, so gradient of f, simplify this as it is copied. So here in place of this we are writing h. So h xk. So this is as it is. In place of this we are writing h xk. This is delta xk. This is equal to 0. Fine. So now take this quantity in the right hand side. So minus, so here we have delta f of xk plus del, in place of delta we are writing h, Hessian matrix at xk, this, and delta xk, this is equal to 0. So now take this quantity in the right hand side. So h xk delta xk is equal to minus delta f of xk. Okay, now this is a matrix, so just multiply by minus inverse. So we get delta xk is equal to minus its inverse in this side. So h xk inverse and delta f xk. Okay, so this is the meaning. So delta xk is minus hk xk inverse delta f of xk. Now what is this delta? This is delta. So now using the forward difference, this can be written as x k plus 1 minus xk. This is forward difference. Forward difference. Okay. So this is equal to minus h x k inverse delta f at xk. Now you can take this in the right hand side. So this will be the formula. Xk plus 1 is xk minus h at xk inverse delta f at xk. This is basically the Newton's formula. This is the Newton's method. Okay. So I hope you understand this method. This is the Newton's method. Okay. Now we will apply this method through this algorithm. So what is the algorithm? So if hkx is positive semi-definite, the approximate function will have a minimum. Okay. So the condition is that this should be positive semi-definite. Then we get the minimum. Okay. Now algorithm is step number 1. Set k is equal to 0. Set k is equal to 0. Okay. And starting point xk is, this is the starting point xk and k is 0. Tolerance is epsilon greater than 0. Determine f at xk. Okay. Compute delta f at xk and h at xk inverse. Find xk plus 1 with the help of this formula, xk minus h at xk inverse delta f at xk. And then finally find the functional value at this point, f at xk plus 1. Now step number 4. If the value of this function at the new point is obviously less than the value of the function at this point, then stop. So okay, f at xk minus f at xk plus 1, this is less than epsilon, then stop. Else compute the next point by setting k equal to k plus 1 and go to step number 2 here. So this is the algorithm. Now apply this algorithm. So example is minimum f at x1 x2 is x1 square minus 2x1 plus 1 plus x2 whole square. So this is our function. The starting point is this, x0 is 0 0. So x1 is 0, x2 is 0. Epsilon tolerance level is 0.05. So now first find out the gradient delta f of x. Delta f of x is this. This is del f by del x1. So just differentiate this function with respect to x1. So what we will get? 2x1 minus 2. So this is written here. At this place we are finding del f by del x2. So just partially differentiate the function with respect to x2. So we get 2x2 only. So 2x2. Okay. Now the Hessian matrix hx. Hx means del 2f by del x1 2. Del 2f by del x1 del x2, then del 2f by del x2 del x1 and del 2f by del x2 2. So after simplification we get 2002. Okay, but here we need inverse. So hx inverse will be 1 by 4. So the inverse of this function will be, this matrix will be 1 by 4, 2002. Okay, that means 0.50, 0.5. Okay, so now compute, here we need the value of the gradient and the Hessian at point xk. What is xk? Xk means x0. So at point 0 0, what will be the value of this delta f of x and the inverse of this? So here delta f of x at point 0 0 is minus 2 and 0. Put x1 0, x2 0. So minus 2 0. Similarly h inverse x at point 0 0. At point 0 0 is 0.50, 0.0 and 0.5, because this is a constant matrix. There is no x1 and x2. Hence this will remain same for all the calculations. Okay. So here iteration number 1. x1 is computed with the help of this formula. So x1 is x0 minus h at x0 inverse delta f at x0. What is x0? x0 is this point 0 0 minus h inverse at x0 is this 0.50, 0.5, this, and then delta f at x0. Delta f of x naught is this value. So 0.20. Now simplify. So we get 1 and 0. Okay. So x1 is 1, x2 is 0. So now find the f of x1. So x1 is 1, x2 is 0. Put it here. So we get 1 minus 2 plus 1 plus 0 square. After simplification, its value is 0. So f of x naught minus, according to this, f of x0 minus f of x1 is, here the functional value is at this point 0 0. When you put 0 0 here, so 0 0 plus 1 plus 0, so 1. So 1 minus at f at x1 is 0. So 1 minus 0 is 1. So obviously this is greater than epsilon. So this is this condition. Hence go to step number 2. So go to the next iteration. So iteration number 2. Now find out the delta f at x1. So delta at f of x1 means this is the delta. So now compute this at point 1 0. So put x1 is equal to 1 and x2 is 0. So we get 2 minus 2 0 and 2 into 0. So 0. Okay. So this is 0 0. Now compute this inverse. This inverse at point 1 0. So h x1 inverse. Since this is a constant matrix, so this remains same. 0.50, 0.5. Okay. Now utilize this formula. So x2 is x1 minus h x1 inverse delta f at x1. What is x1? X1 we have already evaluated 1 0 1 0 minus this h x1 inverse is this matrix 0.50, 0.5. Delta f of x1 is we have already evaluated 0 0, so 0 0. After simplification we get 1 0. So this is 1 0, this is also 1 0. Hence we can say that f at x2 is 0 as it is same value. So now when you find out the difference f at x1 minus f of x2, so 0 minus 0, 0 minus 0 is 0, which is obviously less than this epsilon, and hence stop. So x star is x2, which is 1 0. 1 0 is the solution. So this is the Newton's method. So I think you understand this method. Now in the next video we will start the penalty function methods. In the next video we will start this penalty function method for constrained NLPP. So till now we have considered unconstrained problems, but in the next video we will consider the constrained NLPP. तो नेक्स्ट वीडियो में हम कंस्ट्रेंट एनएलपीपी के मेथड पढ़ेंगे, जिसमें दो मेथड हैं, एक्सटीरियर पेनल्टी फंक्शन मेथड एंड इंटीरियर पेनल्टी फंक्शन मेथड. सो वी विल डिस्कस दिस इन डिटेल इन द नेक्स्ट वीडियो. ओके, थैंक यू.